Okay, so we want to do the problem of linear air drag or viscous drag or whatever you want to call it with no gravity. And I went over a video showing how to solve this. So here's a mass m. It starts off moving this way. It has an air drag pushing back the other way, and it's linear, so it's proportional to the velocity. So we get this air is negative bv. And the solution that we get is that the velocity as a function of time is the initial velocity times e to the negative t over tau, where tau is m over b. Okay, so that's what we have. Now what we want to do is do this with the numerical calculation instead. Okay, so let me see if I can just switch over here. Okay, so here's Glowscript. Let's just start off with a ball. Ball equals sphere. This isn't really super important, but it's going to be there anyway. And it's going to be at the origin. And it's going to have a radius of 0.01, and that's it. Okay. Now, I want this ball to be, I'm going to make it a brass ball in some type of oil. So I'm just going to give it a density. Rho of the metal is 8,500. That's the density of brass. What was that? And so then I'm going to get the mass of the ball. It's going to be 4/3 times pi times the radius, ball dot radius cubed, times the density of the metal. You probably don't even need to do that. Okay. Now I'm going to have, this is the eta. Eta is part of the viscosity. I'm just going to call it 1. And I need to calculate the surface area of the cross-sectional area of the sphere. That's going to be pi times the radius squared. And I need an initial velocity. And I need an initial angle, which I'm just putting in here for later. So now I can put the initial velocity of the ball as a vector. Now you notice here that I'm doing this ball dot v instead of just v. When I make an object like a ball up here, and then I want to give it properties, it's easier to keep track of all the different properties by just giving them this, attaching those properties to the ball. It makes it easier to keep track of everything later. So this is going to be just v0 times the vector cosine theta sine theta 0. That's more than we need, but you know, I'm using vectors. I'm using other things like that, so we can do something else with this later. Okay. So now I'm going to, the other thing I want to do when I deal with numerical calculations, I prefer to deal with momentum. So I'm going to say ball.p, the momentum, is ball.m times ball.v. Now it's the momentum. Finally, I need t equals 0, dt equals 0.01, and that's it. Okay. So let's just say how long do I want to do this? I want to do this, I can't do it forever, and I don't want to do it until the ball stops because the ball doesn't stop. So I'm going to say while the magnitude of the ball, so velocity, momentum, or velocity, this is my velocity, ball.m, is greater than 0.1. Rate 100. This, since I'm doing 100 calculations per second, this line right here in line 17 says don't do more than 100 calculations per second. So that just makes it run right. Now I'm going to calculate the net force on the ball. F net equals, okay, up here I need B. Okay, so let's say B is equal to 6 times eta times pi times A. That's the relationship between the actual viscosity and this parameter B in the force. So it's going to be just negative B times the velocity, but I'm not dealing with velocity, I'm dealing with momentum. So I can say ball.p divided by ball.m. You may think I'm crazy for doing that, and that's fine. Okay, but trust me, it's a little bit better. Okay, so I calculate the force in each step. Now I can calculate the new momentum, ball.p plus f net times dt. So next I need to update the position. Plus, so this is the position, because up here, that's the part of the ball. This will actually move the ball. It's not just R or X or whatever. It's the position of the ball. I need to update that by adding the velocity times dt, but the velocity is going to be ball.p times dt divided by ball.m. Okay, now I need to update time, and I should be ready to run it. Let's run it. It's not running. Okay, I'm going to stop.